In this video, we briefly introduced the low-profile Risley-Prism-Based two-dimensional beam scanning circularly polarized folded transmitarray antenna at Ku-band. The relevant work can be found in IEEE Transactions on Antennas and Propagation. The Risley-Prism's antenna was well developed because it can realize beam scanning in both azimuth and elevation planes easily by mechanically rotating the two gradient phase planes. However, these designs still suffer from high profile because of the large distance between the feed and the transmitarray. Recently, some Risley-Prism's antennas with lower profile were realized by adopting the planar feed source which radiates quasi-plane wave, but their aperture efficiency was lower due to the additional loss in their complex feed network. In this work, we propose an effective solution for the Risley-Prism's antenna to achieve low profile and high aperture efficiency simultaneously. The proposed antenna consists of a circular polarized patch antenna, a metal plate, and two rotatable circular polarization selective metasurfaces. The propagation waves in figure reveals the working principle of the antenna. By mechanically rotating the two circular polarization selective metasurfaces above feed source, the proposed antenna achieves circular polarized beam scanning in both azimuth and elevation planes with low scanning loss. By utilizing the folded transmitarray antenna structure, the overall profile of the proposed antenna is significantly reduced because the wave's propagation path is folded twice times. To further reduce the profile, the feed horn antenna is replaced by a planar patch antenna. The proposed element consists of three metallic layers that are separated by two dielectric layers. By rotating the TX patches of the elements, the proposed element can realize circular polarization selection and tunable transmission phase covering 0 to 360 degrees. The antenna prototype is fabricated and measured. The maximum gain of the antenna at 16 GHz is 22.9 dBi, which corresponds to the total efficiency of 30.1%. The beam scan range covers 0 to 52 degrees in the elevation plane and 0 to 360 in the azimuth plane. The scan loss is less than 3.4 dB within the entire scan range. Since the wave's propagation path is folded, the proposed antenna's profile is significantly reduced. The measured results show that the proposed antenna has good circular polarized beam scanning capability with merits of low profile, lightweight, low cost, low loss, and easy fabrication, which is more suitable for communication systems with limited space and weight.
In this video, I will provide a brief overview of the design titled Multibeam Hybrid Transmitarray based on Polarization, Rotating Metasurface, with Reconfigurable Bidirectional Radiation. This research was collaboratively conducted by Zhong University, Queen's University Belfast, and the Chinese University of Hong Kong. The traditional lens antenna is capable of achieving high-gain beam scanning. However, it is hindered by complex manufacturing processes and high cost. Consequently, planar designs such as transmitarrays and reflectarrays, which offer cost-effective advantages, have become increasingly prevalent in recent years, particularly for their ability to support multi-beam functionalities. Recently, bidirectional beam scanning theory has opened up new possibilities for transmitarray-reflectarray applications. Conventional bidirectional multi-beam antennas frequently encounter limitations due to complex structures, restricted functionality, and significant losses. To overcome these issues, we propose a high-gain, low-power consumption, and simple multi-beam design by using multi-feed array and hybrid transmitarray. The left image depicts our prototype, which consists of three key components: two layers of polarization rotating metasurfaces and a polarization switchable multi-feed array. The transmission polarization conversion metasurfaces serve the following functions: transmission or reflection of the incident wave, generation of pencil beams, and application of polarization rotation. The figure on the right illustrates the polarization selection principle of the proposed HTA, demonstrating that polarized radiation waves can be obtained in both the forward and backward directions. The design operates in three states. In the TA state, the X-polarized wave is fully transmitted through the upper surface for forward beam scanning by optimizing phase distribution. In the FTA state, The Y-polarized wave is reflected by the upper surface polarization gate and transmitted through the lower surface for backward scanning. In the HTA state, a 45 degrees oblique polarization with both X and Y components enables simultaneous bidirectional multi-beam operation. This slide outlines the design principles behind our approach. We begin by designing and analyzing metasurface units with multilayer polarization grids, followed by creating a multi-feed array capable of switching polarizations. Lastly, we determine the phase distribution for both metasurface layers using a bifocal phase design principle. On the left is the prototype fabrication and setup within the microwave testing chamber. The radiation patterns, shown on the right, demonstrate successful low-loss, wide-angle beam scanning across all three operational states. The forward beam scanning achieves a coverage of plus or minus 30 degrees, while the backward beam scanning attains plus or minus 22 degrees. The bidirectional state simultaneously combines the multi-beam functionality of both forward and backward states. The following are the detailed experimental results of the aforementioned design. Compared to previous bidirectional beam scanning designs, our approach offers flexible, low-loss bidirectional beam switching, a simplified beam control method, and low power consumption with a compact profile. This system is suitable for applications in the integrated sensing and communication, wireless backhaul, and microwave sensor networks. Thanks for your attention.
Hello everyone, I'm Wen, and I'm very happy to share our latest research, dual-band omnidirectional scanning array using liquid metal-enabled reflection-type phase shifters. As illustrated in this figure, the dual-band scanning array consists of a wideband 1:8 Wilkinson power divider, 8 dual-band reflection-type phase shifters, and a dual-band dipole array. The phase shifter is built on a dual-band directional coupler. The phase speed is achieved by controlling the path length of the reflected signal using a series of shunt switches that are enabled by liquid metals. A key feature of this work. The equivalent circuits of the microstrip switching elements are depicted in these figures. A wire is inserted in the microstrip line while isolating from the ground by a slot. This is the on state. Its equivalent circuit is a shunt open stub. When the slot is covered by liquid metal, as depicted in the right figure, the wire shorts the microstrip to the ground. This is the off state. With the dual-band coupler and the liquid metal-enabled VPS switches, a reflection-type phase shifter can be realized by using liquid metal as the tuning element. When these VPS are gradually covered by liquid metal, the phase shifts linearly increase from 0 to the maximum. The measured insertion loss is less than 1.4 dB at 1.75 GHz across the phase range of 360 degree, and 2 dB at 3.5 GHz across the phase range of 720 degree. The left figure shows the assembled phased array. Most dual-band antennas are limited to a plus or minus 50 degree scanning range, and suffer from inconsistent beam direction. In contrast, the proposed array maintains consistent beam direction with a wide beam coverage of minus 180 degree to plus 180 degree. The realized gain is about 7.2 dBi at 1.75 GHz and 9.74 dBi at 3.5 GHz. To the best of the author's knowledge, this is the first to achieve the dual-band omnidirectional scanning with consistent beam direction. Thanks for your time.